Hey, I'm thinking of reading Sheldon Axler's Linear Algebra Done Right. And maybe I'll call it Linear Algebra Done Right, Read Right. I was looking at this guy's... Oh, well,
there's a world of
hold
possibility
on.
at your fingertips.
It's very likely
Professor Juan Math does his own reading of Linear Algebra Done Right. But, I think I could offer something a little different from what he offered for the book. However, he does have a link, if I can find it, linearaxler.net. You could get the book at linear.axler.net. If you click on for the PDF file, you can get it yourself. And the good thing about this, actually, see, how do we get this in? There. Is this has the Creative Commons license. So if you go to the Creative Commons license, copy and redistribute the material in any medium, remix, transform, and build. So there's the Creative Commons license. Attribution, well, I'm showing you it's his book. I showed you his website. And I showed you the license, the Creative Commons license. Let's see if we could make this a little bigger here. Maybe I'll read this stuff later. I'm going to call this Linear Algebra Done Right, Read Right. And that means when you read a math book, you don't have to necessarily read everything the first time. Like you could go back and forth between stuff for what you need in the given book that you're looking at. It's good to read all the beginning stuff, of course. Like the summaries here of what the chapter by chapter summary. This book's pretty good book. Top 10 favorite results in the book. That's interesting. 250 exercises. Oh, this is the 4th edition. Vector spaces, let's read that. Linear algebra is the study of linear maps on finite dimensional vector spaces. Eventually, we'll learn what all these terms mean. In this chapter, we'll define vector spaces and discuss their elementary properties. In linear algebra, better theorems and more insight emerge if complex numbers are investigated along with real numbers. Thus, we'll begin by introducing the complex numbers and their basic properties. We'll generalize the examples of a plane and of ordinary space to r to the n and c to the n. That's the real numbers like n-tuples and complex numbers n-tuples, which we then will generalize to the notion of a vector space. So it's ordinary space r to the n, c to the n, and you'll generalize it to the notion of a vector space. As we will see, a vector space is a set with operations of addition and scalar multiplication that satisfy natural algebraic properties. So that's your first informal definition right there. A vector space is a set. It has operations of addition, so addition of vectors, and scalar multiplication. and it satisfies whatever the natural algebraic properties are. All right, so it's for a vector space over a field, I assume the natural properties are the field properties. Then our next topic will be subspaces. That's a subspace of a vector space, which play a role for vector spaces, analogous to the role played by subsets for sets. Finally, we will look at sums of subspaces, analogous to unions of subsets, and direct sums of subspaces, analogous to unions of disjoint sets. Okay, so an analog to the union of a subset are the sums of vector subspaces. And analogous to the union of disjoint sets will be the direct sum of subspaces. Here's René Descartes explaining his work to Queen Christina of Sweden. Vector spaces are a generalization of the description of a plane using two coordinates as published by Descartes in 1637. And here's his fingers pointing, I guess, at the plane. I don't know. All right, R to the n and C to the n. Complex numbers, that's the C. You should already be familiar with basic properties of the set R of real numbers. Complex numbers were invented so that we can take square roots of negative numbers. The idea is to assume we have a square root of -1, denoted by I, that obeys the usual rules of arithmetic. So, what's he saying here? He's saying that I is going to be thought of as the square root of -1. Denoted by I, that obeys the usual rules of arithmetic. Here are the formal definitions. Let's see, complex numbers in ordered pair AB, where AB is in R, but we will write this as A plus BI. Okay, so the standard way to write a complex number is I apologize. I was doing some work and got my fingernails a little dirty there. A complex numbers in order pair AB, where AB is an arm, we'll write this as A plus BI. The set of all complex numbers is denoted by C. C equals A plus BI, which equals A plus BI for numbers A and B in R. Addition and multiplication on C are defined by A plus BI plus C plus DI. Notice when you have A plus BI plus C plus DI, okay, what he's doing is he's taking the A and the C and adding them, and the B and the D and adding them. So that will look like A plus C plus B plus D I. So you add them by coordinate. Also for the multiplication, you should note that this A plus BI, C plus DI, so that's the next thing. Have a little piece of scrap paper when you're reading a book and work stuff out as you're reading through it. So when you're an undergraduate, you learn to FOIL. First, outer, inner, last. Now, this is really the distributive property A times C plus BI and BI times C plus BI. Well, actually, this whole parentheses gets distributed. And then from the right side, you would do C times the A plus BI and the DI times the A plus BI. So what you would get in the end is everything in here multiplied with everything in here. So the first is the A times the C. All right. Here, I'll edit this clip out. So you have A times C, and the last is B times D, I squared. So when you read a book, work with a pen in hand. The outer is ADI, and the inner is BCI. Okay, so this is AC. I squared is -1. So that's like plus -1 times BI, which is just minus BDI, BD. You see an I, so you can distribute the I out. So it's AD plus BCI. Here, I'll put this in parentheses too. And actually, we just showed the AC minus BD is this here, and the AD plus BC is this here. So there's an addition and a multiplication defined on complex numbers. And notice, we used scratch paper and did the work here. And my dirty fingernails here. You could read a math book. Anyway, I guess you are. If A is an R, we identify A plus 0I with the real numbers A. So the real numbers are embedded there in the complex numbers. Thus, we think of R as a subset of C, the complex numbers. We usually write 0 plus BI as just BI, and we usually write 0 plus 1I as just I. That would be like stuff with 0 real number, those would be pure imaginary. It says here in the little, the symbol I was first used to denote square root of -1 by Leonard Euler in 1777. I'll have to remember how to pronounce all these people's names. Oh, look. I can highlight. Sweet. All right. To motivate the definition of complex multiplication given above, pretend that we knew that I squared equals -1, and then use the usual rules of arithmetic to derive the formula above for the product of two complex numbers. Then use that formula to verify that we indeed have I squared equals -1. Do not memorize the formula for the product of two complex numbers. You can always retrieve it by recalling I squared equals -1. Now we use that right here. The I squared is what gave us this negative here. That was I squared equals -1. And then using the usual rules of arithmetic, the next example illustrates this procedure. Okay, so here he's illustrating the distributive property. The 4 plus 5i, this, got distributed to the 2. And, we could use highlighting here. So you see this 2. oh, I used this, I'm sorry, is, well, if I can maneuver this, it's going to be a little bit too much of a pain, I think. So this 2 gets distributed to the 4 plus 5i, which I'll highlight in blue. Up. There. So the 4 plus 5i is right here. Yeah, I don't know how much I'm going to use that. So the 2 goes to the 4 plus 5i, and the 3i goes again to the 4 plus 5i. Alright, well, we'll figure out maybe a good way to do that. And then the 2 will distribute to the 4 and the 5, and the 3i will distribute to the 4 and the 5. And here you notice minus 15, that is my minus BD. Because what he did was 3i times 5i, and 3 times 5 is 15, I squared is where the minus comes from, because I squared is negative 1. Basically, it's like combining like terms. The I term goes with the I term, and the regular real numbers, the integers here, go with the integers. Our first result states that complex addition and complex multiplication have the familiar properties that we expect. So let's look up the definition of a field in math. And let's see, is there an option? Search, let's see, more. All right, the definition of a field. So it has closure under additivity, it has associativity, commutativity, identity elements, and inverses. Let's see. Associativity, identity elements, additive and multiplicative. That's the multiplicative and additive. Additive inverse. Inverses. Every element has an additive inverse. Every non-zero multiplicative. Multiplicative inverses. Right? For every alpha, there's a non-zero. Distributive property. Well, it doesn't say here distributive property. You know what? Let's use Google real quick. Definition of math field. And here's the next thing. You see distributivity is included in the key properties of a field. So I thought it was off the top. I'm doing this sort of off the top of my head, but obviously you have to be a little careful about AI and using the internet, looking up stuff real quickly. But basically, these operations here are giving you a field. So he's going to use the letter F later for both the complex numbers, which is a field, and the real numbers, which is a field. You already know the real numbers have all these properties. Okay, the properties above are proved using the familiar properties of real numbers and the definition of complex addition and multiplication. The next example shows how commutativity of complex multiplication is proved. Proofs of the other properties above are left as exercises. maybe we'll do the proof of this and then do the exercises and then stop. Well, maybe I'll stop the video now and pick up with this and the and some exercises in the next episode. And maybe I'll try and clean my nails here before then. Thank you.